completed his PhD in electrical engineering from MNNIT Allahabad. He has a teaching experience of more than 10 years at different institutes. His research experience is power electronics and drives and its hardware implementation. So, Dr. Soni, I invite
Yes.
you to please start the session.
Okay, sir. So I share my PPT. Is it visual, sir?
Yes, sir,
Yes,
it
it
is
is visible.
visible, sir.
So very good afternoon to all the faculty members and all the delegates. So here I am presenting real-time problems in power electronics hardware implementation and controller interface. So basically, power electronics control system involves different components. There may be the equipments of industries. There may be with the loads, R loads or RL loads or some inductive and capacitive loads. There may be the some motors to be controlled, and it may be the DC motor, induction motors, and other parties, actuators and drivers. So drivers are actually used for improving the power level for the drivers power level for the loads and motor systems. There is another system, the feedback system. Generally the voltage, current and speed, torque, these type of variables are used for the control purpose. So the feedback system provides the these quantities in terms of voltage to be given inside the controller. Measurement system, this is also it may involve the direct sensors or transducers. Power conditioners are required. Analog to digital converters are used for giving the analog inputs to the controller from the sensor and command inputs. And digital to analog converters are used generally for taking the output from the controllers. And there are different types of controllers which may have Arduino and microcontrollers. These are low frequency controllers, and MSP controllers are there. Digital signal processors, digital signal controllers, FPGA based controllers, DSpace and Typhoon Hill types of controllers are used generally in our power electronic control systems. So here is the black diagram of power electronic control system. We can see here that uh, the online variables are fed back to the control current and voltage sensors and other types of sensors which may be with the temperature sensor, humidity sensor, flow sensors, torque sensors, speed sensors. Different types of sensors may be there for feedback to the system. So suppose we have the AC or DC quantities as output in the voltage or current sensors. Sometimes we the controller is type this type we may need the level shifting because there is no negative uh, bidirectional type of input available in the controller, so we may need the level shifting. Some controllers use the differential inputs. We may use the negative as well as positive inputs from the feedback sensors. Also the sensors may need the sensor supply module, which can have the uh, regulator ICs. After this, this is the controller, and after the controller, there may be the driver, and driver is fed from the supply module, driver supply module. Then this driver provides the power to the power electronics controller and the power electronics switches. Some suppose different types of controllers are there. Three-phase inverters may use six switches, and one switch chopper may use only one power electronic switches. So this module is done generally presents the power type of converter and types of switches, and then the output power is provided to the loads and the motors. So here the control concepts and control design platforms are discussed. Control concepts such as PI, PID, and sliding mode, and fuzzy and closed loop, open loop, these type of concepts are used in control concept, control strategies, and this control strategy is used in designing the designing the controller in Xilinx platform or MATLAB or HIL platform, and the simulation model is developed in these platforms, and then the code is generated. This generated code is then coded to the target hardware controller to perform in the real time. So we can see here that during the controller design, first we develop the soft controller inside the platform, that may be Xilinx, MATLAB, or Typhoon Hill, and there will be the feedback sensor, which is soft feedback sensor, which is not external, which is inside the program we have used, and soft power electronics inverter or converter is used, and a soft load, that is the block of motor, it may be the block of the RL is used, and there is a short command inside the PCB. However, suppose we are designing a fuzzy controlled rectifier for driving a RL load. So we have this lower part is the controller and upper part is the power circuit. So this is simple diagram which is used in the MATLAB platform. Now to interface, these are the results. Now to interface these Simulink or soft controllers, we use input and output interface blocks, which is hardware to software platform interface blocks. It may be also used in there is hardware to software interface blocks in Xilinx, MATLABs, everywhere. It is used before interfacing to the actual hardware controller. So also the simulation to controller platform interface block is used. Analog output or digital output is obtained from here. You can see later when we have we can see that the same controller when we are using to generate the code and interface with the real-time controller, we have disconnected this and comment outed all these converter part, because the controllers will generally controllers will generally code for the controller part of the soft platform. So we have the analog input 1 and 2. Here we can also use the soft command also and external command from analog input. We can use both types of commands. If we want to use the command inside the PC, then you can use the lower side of switch, and if you want to use the command from outside of the controller, then we will use the analog inputs. Similarly, when the switches have to turn on according to this control strategy, we have the digital output, and which can be dumped in this code will be dumped in the controller, and the controller will provide the pulses. So this is the interface block we have used for a simple controller. After that, we will generate the code, and this code will be dumped in the controller. After this code has been generated, this Simulink program has been designed, we run on the target hardware. So actually, before this, we prepare to run, and there are various settings. This red colored circle represents where we start the code generation, and after the generation of the code, this whole system will be dumped into this whole hardware controller, and when the command is external command is given, analog to digital converter, that is sampling and hold process, provides the digital input to the controller, arithmetic logic and control unit, and then the output according to this control strategy goes to the digital to analog, and then it comes to the outside for switching or measurement. So this output can be given to the hardware converter, and actual plant is controlled here, and then the hardware sensors provide the output again to the for feeding back to the hardware controller, and the hardware feedback signal is also sampled and holded for getting the in digital form, getting the sensor signal in digital form. So this is three parts actually. We have once we have designed the soft the controller in soft platform. Then we have used the interface blocks to generate the codes, and then generated code has been dumped in the controller, and now this upper block is bypassed, and whole the control strategy of the soft platform will be performed by this controller. Uh, Now we see that there are different types of controllers. Low sampling frequency controllers are Arduino UNO and Arduino Mega 2560, Arduino 3.0. High frequency controllers are there, FPGA, which have nanoseconds of sampling time, and DSP controllers have 90 to 200 megahertz sampling time. Real time controllers are which can also generate the code for RL, and motor types of load. They can also generate the codes for that components. So in a real time controller, the hardware simulation can also be coded. So we can see this FPGA controller and NIPCI 6221 controller in real time. uh, Now how we see the different controllers are here available. We can when we run on target, we select the run on target, we can see the connected controller. Suppose we have connected the Arduino, and then these will be available, otherwise these points will not be available. So once suppose we want to use another real-time controllers like PCI and DSpace. So we have the real-time Windows target, and these type of blocks are available when we have got the package for that controller. So these blocks will be used for Simulink, and then we use the install new board. And when during the installation of new boards, we have different controllers available for which the MATLAB is already designed. Generally, the MATLAB can perform the coding and controller development for all the controllers. So here we can see that any controller, if we have, we first want to add on get the add-ons for that, and get the get the hardware support package. And when we get the hardware support package, we have the available library for that controller. So for Arduino, we have this library. We can see Simulink support package for Arduino, and there are different parts in this library. Just once we have the Arduino is installed in the system, we have to design the ports in this. Suppose our controller is connected to the some port of this computer, then we will have to assign the port. The port can be accessed at the location in the device manager. You can see your Arduino is connected to some port. You can see this information and put your number here. Suppose it is connected in 13 number port, so you will put here 13, then only the controller will work in the real time. So here system target file realtime.tlc is set for uh, Arduino. Similarly, for other types of hardware controllers, the different types of system target files are there. Some ert.tlc and other terminologies are there. So analog to digital converters are the important parts of this controller design. So this uses the sampling and hold process. So higher sampling frequency provides the higher quality of reconstruction of original signals. Higher sampling frequency leads to the higher cost of the controller and higher calculation burden and complexity. However, the precise system needs higher sampling frequencies for fast response control. Once the signal has been accessed by the controller in digital form, the algorithm can be applied, because every feedback or command input is first sampled and then order holded in terms of, and quantization and sampling is completed. Then it is turned in the digital form, and this digital form can be used in the inside the digital inside the soft platform to for all the evaluations. So we use the continuous blocks. The controller in the soft platform will work digitally. So there are different frequencies in the system, that is clock frequencies, hardware sampling frequency, software platform sampling frequency, carrier frequency, and propagation delay in the system blocks needs to be adjusted in terms of increased sampling and controller frequency. So when we are using the more very big system blocks in simulation model, so there will be a larger delay in the system, a propagation delay, and for getting the correct control, precise control, we need to adjust the sampling frequency to higher value to overcome these propagation delays. So suppose we have the signal, suppose we have any signal, then we can use the 5 microsecond for the sampling time for this signal. But we our platform, suppose MATLAB platform is having zero point 0.1 microsecond, then we can use mostly zero point 0.1 up to zero point 0.1 microsecond of sampling time. So higher the sampling time, we will have the higher the information of the signal. So there is a limit that system we can use the maximum sampling time which is allowable by the system soft platform, that is MATLAB or Xilinx. So here one thing is that whenever we use the chopper control or variable duty cycle or fixed duty cycle control, so we have suppose we want to have the lower sampling frequency, then whenever there is a lower, very low duty cycles, the samples of this signal will not be available to sense, because the sampling time is greater than suppose we have 5 kilohertz and a zero point 0.5 duty cycle, then it will be approximately 1 upon 5000 and 0.05 of 1 upon 5000. So this time is for this one pulse, and at least two samples should be there as per the sampling theorem. So we need that 0.05 divided by 5000 divided by 2. This time is required for sampling to get the wave shape of this pulse. So if we use the lower signal frequency controllers, lower frequency controllers, this small pulse will not be detected. So also we can see here that for you can see different patterns of triangular waveforms. So for steep waveform which has less uh, uh, higher frequency, will need the higher sampling frequency, and in the middle you will need the lower sampling frequency, and in the last you can need the lowest sampling frequency for the signal detection. So higher the signal frequency, we need higher the controller and platform frequency. So switching frequency, simple converters need lower signal frequencies such as 1 kilohertz to 20 kilohertz, such as inverters and choppers. Resonant converters need generally 50 kilo to 10 megahertz signal frequency for output. So for matching these uh, high frequency signals, we need the higher frequency drivers and higher frequency controllers to get the appropriate control. So in the sampling frequency should be very high, and driver frequency should be very high. So digital to analog outputs are there, which are used to generally get the analog output from the we can get the analog output from the controller. Suppose we have the pulses to given to the hardware power electronics converter, then we will need only the digital output from the controller, and we will not use digital to analog converters. Sometimes when the speed variation is there and we want to code sometimes according to the speed, there is some pulses are to be given. This uses the analog to digital. However, we have the digital input inside the controller and we need the analog output. Then we will use the digital to analog converter. And the another part of the power electronics converter control is switch selection and data sheet. So generally the switches has the most important part, most important parameter which has to be seen, that is forward blocking voltage and on and off state leakage current, maximum current rating at 25 degree, and current rating increases at the high temperature. Means whenever the switch is heated, we have the higher current passing through the device, and so the device with higher current rating only can withstand that condition, otherwise it may fail. So during the design, we assume that the device will be in the heat condition, therefore the selected device must be at least twice the current rating for normal operation. Suppose we have the normal operation of 5 ampere, and we as always assume that it will not work on 25 degree, always it will heat. So how much heat will be there according to the load current and RDS on resistance, we can use the power dissipation. How is the power dissipation in the power electronics switch. Then depending on this power dissipation and parameter, just 1 minute, I have interruption. uh, Okay, so parasitic capacitance of device, on state resistance of device, these all parameters are necessary to observe before selection of the switch. So here we can see the data sheet of a MOSFET. Here we see that the low RDS on means whenever we require for efficient control and high efficiency converter design, we need the low RDS on. And here ID is 220. We can see this means we have the current rating of 220 in forward direction in case of the turned on condition. So according to our required control and cost adjustability, we can select the switches. So suppose we want the 70 volt of forward voltage, then we cannot use this switch because it has the forward breakover voltage only 60 volt. So off state voltage is 60 volt, and we have the 70 volt of applied voltage, then it will not withstand in off state. So the higher voltage rating switch has to be used. So here you have drain to source voltage, that is 60, gate to source voltage continuous, we can use the 20 voltage plus minus pulses. And we have the continuous drain current. We can see here that at condition of 25 degree 220 ampere it is drawn. However, at condition of 100 degree it has reduced current rating, that is 156, and if it increase then 156, it will heat and it will deteriorate. So according to the temperature, the rating of the current rating of the switch decreases. Power dissipation, so at 25 degree the 283 watt of power dissipation will be there. And pulse drain current, here you can see that if 660 ampere is appeared 660 ampere is passing for 10 microsecond, the device will not deteriorate. However, if it increases for time, or it increases for the magnitude, then the device can deteriorate. So current limited by package, that is 130 ampere we can provide according to the package. And operating temperature range, so here we can see that minus 55 to 175 degree centigrade it can work. However, we generally don't keep our devices in this higher ranges. So we have another this point 0.53 degree centigrade per watt. Suppose we have RDS on and the current in the system, which is according to that we can calculate the I square RDS on in the on state power loss in the device. And if that is higher watt, then there will be a percent higher degree centigrade that will be added to this, and higher temperature rise will be there. So here you can see the drain to source voltage. Drain to source voltage is 60 volt. This is minimum. Minimum means uh, it is if you increase then 60, it will deteriorate. Drain to source breakdown voltage. If you breakdown voltage temperature coefficient, millivolt per degree centigrade. This is 6.1. And here off state leakage current you can see here at 25 degree centigrade, off state leakage current is 1 microampere. If you increase the temperature, the off state leakage current will increase to 100 times. So gate to source leakage current, if you don't apply the voltage to the switch, forward voltage to the switch, and only apply the gate, then there will be a leakage current in the gate to source, that is plus minus 100 nano ampere. Also on characteristics, we can see that gate to source voltage is threshold voltage, means after this 1 volt and 250 microampere the gate will start to means gate activation will start. Maximum is 3 volt and minimum is 1, means after 3 volt it will start, means after 3 volt it must start within this range. Threshold drain to source on resistance, yeah, this is very important parameter. And before selecting the device, we generally see this lower the RDS on, better is a switch. And we have another important parameter, that is forward diode voltage. This is the reverse recovery diode. It is anti-parallel to the forward direction of this MOSFET. And we have a very important parameter, that is reverse recovery charge time, discharge time, reverse recovery storage charge. So according to these times, we decide what should be our frequency. Here we can see turn on delay time, rise time, turn off delay time, and fall time. Add together this time, and depending on that you will get a frequency. So our frequency should not be more than that. Okay. If we use the turn on turn off frequency greater than the frequency obtained by this timing, the device will remain on the turn on mode or turn off mode. So it will not work properly. So device the frequency of switching given by the controller and driver should be greater than the should be lower than the frequency obtained using this timing. So adding total time, we can get a frequency for switching. So uh, this is all about switch selection. Now we have the driver circuits, and IGBT drivers are different from the MOSFET drivers, because it may need the to discharge the stored charge in the IGBT. So a negative pulse of -5 to 10 volt is also used. And generally 67135 used for 5 kilo up to 5 kilohertz, and for higher frequency TLP 250 is used. For more higher frequency, we can use the data sheets of the different driver ICs, and we can select the driver IC depending on their frequency ratings. So this is a driver circuit. Generally it is the upper diagram has taken from some reference, lower diagram is also taken from some reference. We can use this driver IC for using driving the MOSFET. So sensors and feedback, there may be the different sensor. Always the sensor provide the quantities in terms of the voltage, and this voltage is input to the controller, and the algorithms will be done inside the controller according to the voltage level. And here we have suppose the design of current and voltage sensors need predefined voltage to voltage ratio, current to current ratio. Suppose we have 300 volt primary side, and we need the 10 volt maximum for the controller, then we have to keep 300 by 10 volt ratio for voltage sensor. So our voltage sensor attenuation will be 10 by 300, and later it is when it is used in inside to take inside the converter, we use a block as a gain in the simulation model to multiply it by 300 by 10, so that original value is obtained inside the simulation model. So any queries you have, all of the audience, if any queries are there?
Thank you, Soni sir. I think there is no query. Thank you so much, sir.
Thank you.
Participants, we have validity session at 1 p.m. So please leave this meeting and join the validity session. Participants, please join the validity session.
Those who are connected in online mode,
Yeah.
they will be here, I think.